Hi there and welcome to Heavy Maths. It's Mr. Arnold here and this is the 8th video on sequences where we're going to take a look at convergence. Now it is, as always, geared towards A-level classes but is applicable to lots of other maths modules too, so hopefully you find this video useful. Okay, now we talked about convergence in a previous video and what we're going to look at now is what happens if we add up a geometric sequence or a geometric series forever. What would happen? So let's consider this geometric series here. So 1, a half, a quarter, an eighth. You're going to have a 16th next and so on and so forth. What would happen if I was to add this up to infinity? So I'm going to add, if n was infinity, what would the sum of the series be? So suppose we work out, well, what is the sum of the series going to be equal to? We're going to use the usual formula, a times 1 minus r to the power of n all over 1 minus r. Now you might notice I'm using this version of the series because the common ratio here is a half. So r is between -1 and 1. You could use the other formula, but this one is a little bit easier to use, so I'm going to use this one. The value a is going to be equal to 1. So let's see how that affects our sum. So substituting in, we're going to have a is 1. We're going to do 1 subtract r, we know is a half, to some power n, and that's all to be divided by 1 minus a half. Okay, let's expand this out so we get 1 minus a half to the power n over a half. Now I don't like dividing by a half, so I'm going to multiply the top and bottom, the numerator and the denominator by 2. To get rid of that half. So that's going to give us, so multiplying above and below by 2. 2 times 1 is 2. And now I'm going to do negative 2 times a half to the power n, like so. The denominator, when I multiply that by 2, we're going to get 1, so dividing by 1 is just the same as the numerator on its own. Now let's see if I can do something with this here. Okay, the first value is still 2. Still going to have this minus sign here. But I'm going to write a half in a different form. I'm going to leave the 2 on the outside. And instead of writing it as a half to the power n, I'm going to write it as 2 to the power of negative n. So using the laws of indices to manipulate this guy here. Okay, so we still have the first term being 2. Now, minus, when I do 2, so the base 2 times 2, so the base is the same when we're multiplying them, so we should add the powers. So I should have by 2 to the power of negative n plus 1, because this term here is 2 to the power 1. So you're doing 1 plus negative n, so we get negative n plus 1, like so. And then finally what I'm going to do is I'm going to write that as 2 minus, and I'm going to put it back in the form we had to begin with. So instead of writing it as 2, I'm going to flip it using the laws of indices, write it as a half. But if I do that, I need to change the sign of the powers, and we get n minus 1. And then very last thing, so we get 2 minus, if I've got, so on the side, if I have a over b to the power of n, that's the same as a to the power of n over b to the power of n. And 1 to the power of n minus 1, doesn't matter what it is, what the value of n is, we will always get 1. And then the denominator, 2 to the power of n minus 1, well, we have to leave that as it is, 2 to the power of n minus 1. Okay, so this is our expression for S of n. Now I'm going to think what happens to this as n gets bigger and bigger and bigger. So as n tends towards infinity, let's try to get that infinity symbol correct. As n gets bigger and bigger and bigger, what's going to happen? Well, we're going to have 2 minus, and if n gets larger and larger, well, let's consider a small value of n, such as, I don't know, 1. If n was 1, you'd have 1 take away 1, which is 0, and 2 to the power of 0 is 1, so you'd have 2 take away 1. What if n was 3? You'd have 3 take away 1, which is 2, and 2 squared is a quarter, so you'd only be taking away a quarter. What about if n was 5? 5 take away 1 is 4, and 2 to the power of 4, 2, 4, 8, 16, so I'd only be taking away 1/16. So as n gets bigger and bigger and bigger, as n gets bigger and bigger and bigger, this fraction here gets closer and closer and closer to 0, so you end up with 2. So what we can say is the sum to infinity of is going to be equal to 2, because this fraction here is getting smaller and smaller and smaller. Okay, so let's consider a general situation. Suppose I want the sum to infinity. Let's just consider the sum to the sum of the values n. Well, we know that that's a times 1 minus r to the power of n over 1 minus r. Let's expand it out now and see what happens. That's going to equal a minus a times r to the power of n over 1 minus r. So now what I can do is, let's separate it. So we're going to have a over 1 minus r subtract a to the power of r, a r to the power of n over 1 minus r. So if I had, imagine I had 2 take away 3 over this, I could write it as 2 over this, take away 3 over this. Okie doke. Now, consider what happens if r is between negative 1, in fact, let's write it underneath. If r is between negative 1 and 1. So we say if r is numerically less than 1. So for really, really small values of r, I'm going to end up with this part here. I'll highlight it. Let's get the highlighter out. If r is between minus 1 and 1, all of this part here actually heads towards 0. So all of this here that I've highlighted is going to tend towards 0. Why? Because r to the power of n tends towards 0. Because I'm going to have a very, very small value here. So it's going to tend towards 0, which means that the sum to infinity must be equal to, in general, a over 1 minus r, provided that r is between negative 1 and 1. So that's what this means. The modulus of r is less than 1, which is essentially the same as this. So this is the formula that we're going to use to work out the sum to infinity. Now, just before I move on, just one thing maybe that I didn't make very clear there is, if we consider that the reason, if r is between negative 1 and 1, so suppose r is 0.5 for example, and so suppose r is 0.5 and n is getting bigger and bigger and bigger. If I do 0.5 squared, I'm going to get 0.25. If I do 0.5 cubed, I'm going to get, let me think, 0.125. So you can see that the numerator here is going to get smaller and smaller and smaller as n gets bigger and bigger and bigger. And if the numerator is getting smaller, then the whole fraction is getting closer to 0. So just to clarify there what was going on. Okay, we're going to look at an example next. Okay, so first thing we're going to do is work out the common ratio r. Hopefully you can see the common ratio r is 1 over 3. You can take any term and divide it by its previous term, you should get the common ratio. So essentially we're multiplying everything by 1/3. A we can see is 1, and now we're going to use the formula, the sum to infinity is going to equal a over 1 minus r. And that's provided that r is between -1 and 1, which it is. So in this case, it's going to be 1 over 1 minus 1 over 3, which is going to equal 1 over 2 over 3. And just moving along here, I'm going to multiply above and below by 3 over 2, which is going to give us 3 over 2. So this geometric series tends towards 1.5. Okay, an example 2 now. We're told that the second term of a geometric series is 16 and its sum to infinity is 100. Find two possible values of the common ratio and the corresponding first terms. Now the second term of a geometric series is 16. Remember, a geometric series goes a times r squared, and so on and so forth. So that means that a times r must be equal to 16. Okay, so that's one piece of information. In fact, I'm going to call that equation 1. Now we're told that it's sum to infinity. So if I sum to infinity, in fact, let's change the color to blue. Sum to infinity is equal to 100, which means that if I do a over 1 minus r, we're going to get equal to 100. And what I'm going to do now is I'm going to multiply both sides by 1 minus r, so we get a is going to equal 100 times 1 minus r. Let's call this guy equation 2. Right, now hopefully you can see here we've got two unknowns, a and r. We've got two equations. It's got to be a simultaneous equation. So what we're going to do is we're going to substitute into equation 1. We know what a is. A is 100 times all of this. So instead of a, I'm going to do 100 times 1 minus r times r must equal 16. Okay. When we tidy this up, we're going to get 25r minus 25r squared is going to equal 4. So I've divided everything by 4 and expanded the brackets in one go there. Right, let's rearrange things. So we get 25r squared minus 25r plus the 4, got to equal 0. We got a quadratic here. Okay, so if I do 25 times the 4, I'm going to get 100. You actually could use your calculator to solve this if you've got one that does so, but I'm going to factorize it. When I factorize it, we're going to get 5r minus 1 times 5r minus 4. That must equal 0, which implies that r must equal 1 over 5. Or it could be equal to 4 over 5. Now both values we can see are actually between -1 and 1, so the sum to infinity does exist. So if r equals 1 over 5, that means that A is going to equal, let's see, A must equal 16 over R must equal 80. The 16 over 1/5 is the same as 16 times 5, which is 80. And if, say, R equals 4/5, well, that implies that A must equal 16 over R. So 16 divided by 4/5 is the same as 16 times by 5 over 4, which is going to give us 20. So if A is 20 and R is 4/5, or A is 80 and R is 1/5. And in case you're wondering where these values of A have come from, we're using this formula here. Let's just show you. A must equal 16 over R. So we're using that formula there and substituting the value R in to get A. Okay, that's it for this video. Hopefully you found it useful. We'll be back again with another video soon. All the best and good luck with the revision.